Okay, so the next lecture is on autoencoders. And in the previous lecture, we saw that how we can use classical computer vision algorithms to extract features from images, right? We studied HOG, histogram of gradients. We studied SIFT features. We studied how we can detect key points in your images. Now, autoencoder, it's kind of, we are shifting gears and we are moving from classical computer vision to, let's say, the learning-based approaches or data-driven approaches, which is towards deep learning. And of course, there are a lot of different ways to extract features in deep learning as well. Autoencoder is one of them. And it's like one of the simplest way as well. So we'll start with this. Okay, so the core idea of autoencoder is, as the name suggests, whatever input you have, you learn features from that input, and then you try to reconstruct that input. Okay, so that's the core idea. And the way you do this is, you have your input sample and you try to learn some meaningful features. Okay, and using that could be fully connected layers, that could be your CNN convolution layers, or like any other way. So you learn those features and then you use those features to again reconstruct that input data. And if you're able to do that, it means the features are good, because then they're capturing the information about your input sample, right? That's why they're able to reconstruct it. Now, some key features here should be, when you are learning those features, the size of those features should be pretty small as compared to your input data. Otherwise, what you can do is you can just copy like all the pixel values. Let's say if the input is image, you can just copy all those values, and you say that, okay, this is my feature, and since you have just copied, you can do the reconstruction as well. Okay, but those are not good features. So what we want is, we want like features in a compressed format where the number of values is like far less than your input dimensionality. Now, another interesting aspect of autoencoders is this falls like somewhere like in unsupervised learning regime. And the reason is, you don't need any annotations. All you need is data. If you have some image, you don't need any annotation on that. You don't care like what objects are present in that image, because you don't need those labels to train the model. You have the data point, let's say you have the image. All you need is the same image itself, like to train your model, because you will train your model using reconstruction loss. Okay, so this is kind of not completely unsupervised, because you have a loss function to train it, but unsupervised in a sense that you don't need annotations. Okay, but still you will have a loss function, you will compute the loss values, you will compute the gradients, and you are going to train your model. Okay, so you have that supervision in autoencoders. Okay, so supervised, as I said, you will need some kind of labels or annotations. And one simple example is, if you are doing image classification, for each image, you should know what object is present in that image to be able to train your model. The basic architecture you have for autoencoder is, it's just basically two parts. The first is encoder, the second is decoder. And again, this is just at conceptual level. I mean, you can have any kind of encoders, you can have any kind of decoders. And again, it depends on the data. Okay, so autoencoder, it's not like very specific to images. It can be applied to any domain. If you have video, then you can have autoencoders. You can have autoencoders for like text kind of input as well, for language, or maybe audio signal. Okay. So the basic structure looks something like this. You have this input data. In this case, it could be some feature vector, it could be images, it could be a video, and you have your encoder head, which takes like this as input, and it tries to like compress that input to a very small like dimensionality space. Okay, so that's called the code. And then what you do is, you use that code to again reconstruct the same input, which is shown as x prime here. Okay, so when you do that reconstruction, then what you can do is, you can actually estimate how good that reconstruction was, because you have that input here. Okay, so you can just compare like this input with the output, and you can use that to compute your loss. So that could be your training loss when you train this kind of model. Okay, so this part is called encoder, and this part is called decoder. So this will be like the basic structure of any autoencoder you design. Now, I think in one of the lectures, we were also talking about PCA and singular value decomposition, where we saw that PCA is like a very good way to compress your features and to represent your data samples. And we also discussed like how that was used when I think the first time we went to Moon, the images were sent, like their PCA was used because the images were compressed and then only few values were sent over and then the image was actually reconstructed. Okay, so PCA is very, very powerful and effective in that. And in that sense, it has like correlation. You can say like some kind of relation to PCA, because even in autoencoders, we are trying to compress the size of the features, right? So we are only trying to learn very, very important set of features, which are sufficient to actually do the reconstruction. Right, so there's some comparison you can make between these two, which is I think fine, because PCA, the idea is you try to learn like the most prominent, you can say like most prominent properties you have in your data. And then you do some kind of linear combination of those properties to define your objects. And autoencoders, it's like trying to do the same thing, but in this case, we are trying to actually learn it from the data, right? In that case, it's not learning, you're just extracting what is there. Okay, PCA, I mean, it's a known algorithm, right? You have certain set of steps, I mean, there's no learning involved. Okay, so what you can do is you can define your encoders and decoders from an autoencoder as a function. And let's say your encoder is function f, and x is your input. So you will send your input to the function f, the encoder, and h, let's say, is your latent space. Then let's say this is your original input image, x. F is your encoder function. Then this will be your latent representation. And then again, you can represent your decoder as a function where you send in like this latent code as input. For example, in this case, like G is your decoder, and which will give you R, which is the reconstruction of the input. Okay, so in this case, it will try to reconstruct 4. Now, again, you can have a lot of variations of autoencoders. You can have shallow autoencoders, which means like only few layers. In this case, you just have one layer in encoder and one layer in the decoder. Or you can have very deep networks where you can have several layers in your encoder and several layers in your decoder. And most of the time, it's kind of asymmetric. You have like similar kind of structure on the encoder, and you just try to mimic that while you decode your latent code. But of course, that's not like a requirement. You can have variations there as well.